This is Metin with Ozen Engineering. We are going to start our webinar on linear and nonlinear dynamics. Thank you for joining us today. Our company, Ozen Engineering, is an ANSYS channel partner. We've been ANSYS channel partner of the year in 2015 as well as 2018. And we are an ANSYS Elite channel partners. We're involved in software sales, training, technical support, and consulting services. So we sell all ANSYS products, fluid structures, multiphysics, electronics, and optics. In addition, we have a cloud service that we call Ozen Cloud, where you can run ANSYS. And we also enable VR, virtual reality, with ANSYS tools as well. Our webinar schedule today, April 10, that's linear and nonlinear dynamics. Next week, April 17, turbulent flow with ANSYS CFD. And April 24th is fracture mechanics. And there will be more coming after we review what we want to do next after in the month of May. So please visit our website, ozeninc.com/training for free registration. And you can find the recordings of previous webinars under ozeninc.com/webinar-library. And you can also register for our newsletters for monthly ANSYS updates. And this session will be recorded, is being recorded, and it will be available on this website, ozeninc.com/webinar-library. So we are also hiring an electrical engineer with HFSS experience. If there's anyone out there that you know would like to join us, please apply at info@ozeninc.com. So today we are going to talk about dynamics, but before we get into that, I just want to go through this. You know, finite element analysis is really split into an implicit and explicit simulation. So implicit simulations is where if you have an event that's happening really fast, then you may want to look into explicit simulations, and that's why we're looking at like car crash here or a drone crash in the lower right-hand corner. So if there's an event that's happening on, and this is not hard in stone, that's it says 100 milliseconds, but something that's happening really fast, and you may want to look into explicit solutions. Implicit solutions is for an event that takes longer in time frame. You can actually use explicit methods for in some implicit cases, and implicit methods in some explicit cases as well. So this is not a hard division, but in general, this is a good guideline. ANSYS Dynamics. ANSYS is an implicit code, so we will be talking about ANSYS implicit dynamics today. We have separate webinars on ANSYS explicit dynamics or ANSYS LSDYNA. So we have two different codes on the explicit domain. One is ANSYS LSDYNA, the other one is ANSYS AutoDyn. So, as you know, in a structural analysis, we are not talking about dynamics right now. In a structural analysis, the structural analysis could be linear or nonlinear. And when it comes to nonlinearity, there are really three sources of nonlinearity. One is large deflection, the other one is contact nonlinearity, and the last one is material nonlinearity. And in the problem in the upper right-hand corner over here, what we are looking at is we have all these three nonlinearities taking place in this animation here. We have large deflection, we have contact nonlinearity, there's actually self-contact, and also there's material nonlinearity. So when we look at implicit FEA and ANSYS dynamics, the routine that we really need to go through is if and when we are going to do a dynamic simulation, we should always start out with a modal analysis. In a modal analysis, we first do a modal analysis to determine the natural frequencies as well as the mode shapes. And why is that important? Because the natural frequencies and the mode shapes are used in further simulations. After a modal analysis, we can look into transient dynamic analysis, and transient dynamic is in time domain, or after modal analysis, we could go into harmonic response analysis, and that's in frequency domain. So after a modal analysis, we can solve our problems either in time domain or frequency domain. And from what do we use from the modal analysis? From the modal analysis, we determine the natural frequencies. And this means that if you are going to do a transient dynamic analysis here, we get the natural frequencies of interest from the modal analysis, and we say 20 times, 1 over 20 times the natural frequency is going to give us the time step size, the initial time step size, if we are going to solve our problems in time domain. And if we are going to solve our problems in frequency domain, then from the modal analysis, when we determine the natural frequencies, then we can focus on what's the beginning frequency and what's the ending frequency for the frequency domain simulation. And under frequency domain, there's also response spectrum and also random vibration simulations as well. So today we are going to go through modal, we are going to go through harmonic response and transient dynamic analyses. We are not going to touch the response spectrum or PSD, but these are really important topics as well. In the future, we are going to have a session on just implicit FEA dynamics, just focusing on these response spectrum and PSD simulations. So please keep in mind, whatever we see on the right-hand side, including modal analysis, harmonic response, single point or multi-point response spectrum, PSD, these simulations are linear only. And what do we mean by linear only? That means there's no nonlinearity. However, if we solve the problems in time domain, then the problem could be, we can solve it either in a linear manner or in a nonlinear manner. And just to review again, when we say nonlinearity, there are, again, three sources of nonlinearity: large deflection, contact nonlinearity, like frictionless or frictional contacts, and material nonlinearity. Anything that has to do with creep or viscoplasticity, or large, any material nonlinearity that you can think about, it goes under this here. So again, in a implicit dynamic simulation, the right-hand side, the modal, harmonic frequency, single point response spectrum, random variation, these are all linear only. There is no nonlinearity involved here. If you would like to involve any nonlinearity, being contact, frictionless, frictional contact, or material nonlinearity, or large deflection nonlinearity, you have to do transient dynamic analysis. And that means you have to solve the problem in time domain. Okay, so with that, let's go and take a look at the introduction to dynamics. So as we have seen, static structural analysis, it will do just steady-state load conditions. However, dynamic and structural analysis is going to take into account inertia and damping. So if inertia and damping are important, then we have to do a dynamic structural analysis. So so in a vibration analysis, of course, there's the famous Tacoma Narrows Bridge, which collapsed under just under 42 mile per hour winds back in 1940 years. And on YouTube, there's really a nice video of this bridge collapsing. This kind of brings the urgency. As an engineer, we need to understand the dynamic behavior of the structures that we are designing and that we are building. So we need to do a free vibration analysis. We need to do a forced vibration. We need to look at seismic shock loads. And what are those? Those are examples of earthquakes or blast loads. And random vibrations. If you have lately, random vibrations is being done a lot in with transportation of sensitive equipment like lasers. As you're transporting these laser equipment, you put them on a truck bed and you ship them from one location to another, and maybe you put them on an airplane, ship it overseas. This sensitive equipment like lasers, like MEMS devices, they get subject to these random vibrations, and we can do these simulations in ANSYS. And like I said, we are going to cover this in a different seminar as well. We will have a different webinar on this. So modal analysis, this is strictly used to determine structures' vibration characteristics, natural frequencies, and mode shapes. And after that, we have an option to do a harmonic analysis, and this is looking at the structure's behavior in frequency domain. When we have, for example, rotating machines, if anything rotating, then then we can analyze that. It's in frequency domain. Response spectrum. Response spectrum is where you can do a very quick simulation to understand how your structure is going to respond to events like earthquakes, to shock and impact loads. And random vibration, again, this is used to determine how a component or how not only a component, how an assembly responds to random vibrations. And this is, again, it doesn't have to be just space application. It could be anything from transportation on a truck bed to transportation in an airplane. Transient analysis, this is in time domain. So this transient analysis can be used to calculate structure's response to time varying loads. So in kind of a summary here, the modal analysis as an input, you don't need to have any input to modal analysis. You can actually take apart, bring it into ANSYS, and without applying any loads, any displacement boundary conditions, you can do a modal simulation. What's the output of this? Then what we do is we get the natural frequencies and the mode shapes. And if there's any need, we can also get stress-strain profile. Any nonlinearity involved? And like we said, no, there's no nonlinearity allowed in modal analysis. This is not an ANSYS limitation, by the way. This is just finite element methods in action, just the formulation. Any program out there that does FEA, modal analysis, there's no nonlinearity involved, because we will show you the formula, the differential equations that's being solved. It just doesn't allow any nonlinearity. Harmonics. In a harmonic simulation, again, this harmonic simulation is done in frequency domain. The inputs are any sinusoidally varying excitations. That would be the input, like force or displacement. So you can input anything that's any loads that's varying sinusoidally, then that could be an input. And the output, of course, if you will be sinusoidally varying response of the structure at every single frequency. And again, there's no nonlinearity. Spectrum and random vibration simulations. In a spectrum analysis, you would input a spectrum, an earthquake spectrum, for example. That would be the input. And then as an output, you get the maximum response of the model when it's subject to this time history. And again, there's no nonlinearity. Random vibrations, in this case, you would input a probability distribution of excitation. These are called PSD, power spectral density excitation curves. And usually, this says the vertical axis in a random vibration input is G squared per Hertz. And then as an output, we get probability distribution of response, meaning that we get displacement stresses as either 1 sigma, 2 sigma, and any sigma values, ANSYS will calculate. And again, no nonlinearity. And the only nonlinearity, again, is in the transient time domain simulation, where you would input time-varying loads and you would get a time-varying response, meaning that your inputs are in terms of forces as a function of seconds or milliseconds or minutes, and your output will be displacement stresses as a function of time. So, so here are some categories that we often hear when we speak about dynamics. For example, a shock analysis. We do a lot of shock simulations for where the inputs are basically, it may be G's or RMS G's, or it could be a drop test simulation, a drop shock simulation. So the shock analysis, if it's just G's, you can handle it in a static analysis. Or if you're doing a drop test, then you have to do a transient simulation, and that's in time domain. Free vibrations, you have to do, you know, a modal analysis. So free vibration and modal analysis are often almost always used in the same context, where we are looking into the natural frequencies and the modes of vibrations and the mode shapes. And when we say vibration, if it's an earthquake, seismic, any type of response spectrum input, then we do a response spectrum analysis. If the vibrations is sinusoidal, where we are looking into sine sweep, frequency sweep, or rotating imbalance, then we would do a harmonic analysis. And if we are talking about a random vibration event, where we are given a PSD, power spectral density curve, then we will do a random vibration analysis. In ANSYS, by the way, right now we are running ANSYS version 2019 R1. ANSYS, as you may know, this year they changed the format. Instead of calling version 18, version 19, now this year we switch over to the year. So the current year is 2019, so we are working with 2019 R1. In a given year, ANSYS releases 3 versions. R1 usually comes out at the end of January, and then R2 comes out about May, June timeframe, and R3 will come out August, September timeframe. So in Workbench, as you see here, for example, we have the modal analysis here. If you double click on it, then you're going to, ANSYS Workbench is going to bring up the modal template to do the modal analysis. Then, if you would like to do a harmonic response analysis, then the template's over here. You double click on it. That's the harmonic response analysis. And if it's transient dynamic analysis, then it would be transient structural analysis here. So these would be the three different, and also, of course, here we discussed response spectrum. Response spectrum is over here, and also random vibration. All of these are given here. So today we are going to talk about modal, and we will talk about harmonic response, and also we will talk about transient dynamic analysis. So, what's the general equation of motion? What are we solving? This is the nonlinear governing equation for transient dynamic analysis, meaning that the first one, mass matrix times U double dot, is the inertial forces. Damping matrix times U dot, which is velocity, is the damping forces. And then we have K times U. K is the stiffness matrix. These are designated as the stiffness forces, is equal to the applied forces on the right-hand side. Here it's given as a function of time. So this would be the transient dynamic analysis. Why? Because this equation is given as a function of time. That means we'll have to solve this as a function of time. So where's the nonlinearity come in? The nonlinearity comes in the stiffness matrix. And that's why, as you see here, the mass matrix, the damping matrix, they are not as functions of U or U double dot or U dot. The only matrix here that's a function of the displacement is the stiffness matrix, which is K. And this is where the nonlinearities come in. And again, we discussed this, that the sources of nonlinearity are large deflection, and it is nonlinear contacts, and it is material nonlinearities. And again, this is really important. Nonlinearity is allowed only in a full transient analysis. Only in a full transient analysis, that's where nonlinearity is allowed in this equation here, which, as you see, it's a function of time, and the nonlinearities appear only in the stiffness matrix. So this is kind of important it's important, and we should emphasize this because the question always comes up as to, can I do a modal analysis with frictionless contacts? And the answer is no, because frictionless contacts are nonlinear, and we can only do a modal analysis with linear contacts. And what are the linear contacts? Linear contacts are bonded contacts. So we cannot do a modal analysis with frictionless contacts. So same thing with harmonic analysis. With harmonic analysis, we cannot do a frictionless contact or a frictional contact. It has to be a transient dynamic analysis. And this is where those nonlinearities will go into. Okay, so given that, we are going to switch over to the modal analysis over here. Again, the modal analysis is used to determine vibration characteristics, meaning that natural frequencies and mode shapes. Those are the two most important ones, natural frequencies and mode shapes. And it should precede any type of dynamic analysis. And another important thing, keep in mind, modal analysis structure is linear. Mass matrix and stiffness matrix are constant. They are not functions of any nonlinearity. And in a modal analysis, we do not apply any loads. If in ANSYS you go in and you try to apply any force in a modal analysis, you will see that they're all grayed out. So you won't be able to do that. So what's the equation that we are solving? Remember the equation in transient dynamic analysis, we have mass matrix times U double dot plus damping matrix. So the damping matrix kind of disappeared here. We only have mass matrix times U double dot, stiffness matrix times U is equal to 0. The right-hand side is 0. Why is that 0? Because no loads are allowed in a modal analysis. So by the way, this brings up a question. How can we do a pre-stress modal analysis, right? Pre-stress being you may be applying some type of a load on a structure, and after you apply the load, you would like to know its natural frequencies, because the natural frequencies are going to change in a structure, especially if you have bolt loads or any other loads in the structure. To do a pre-stress modal analysis, we first do a static structural analysis like you see here, and after that we drag and drop modal analysis into this. So now from the static structural analysis, we are actually bringing an additional stiffness matrix over here, and then the modal analysis that we do here is going to be very much dependent on how much load that we apply in the static structural. And of course, the modal analysis results will change depending on the magnitude of forces that we are applying or of loads that we are applying in the static structural. So this is the format to do a pre-stress modal analysis. And what we are discussing here is without pre-stress, just to do a natural frequency simulation over here. So to solve this equation where the right-hand side is 0, we assume that there's harmonic motion. And as soon as you assume a sinusoidal motion, that makes the problem nonlinear. That's the source of linear assumption, is that this is being solved as a linear sinusoidal excitation. So harmonic motion. So we are assuming that the displacements are as a function of sine omega t, and you take a double derivative of this, then you get minus omega square sine omega t, and then you're left with this equation over here, which is, this brings up that famous equation F is equal to square root of k divided by m under the square root sign. So that is the source of this. That's where that famous natural frequency comes over. Natural frequency is equal to k over m under the square root sign. So the solution of this is going to give us the eigenvalues and the mode shapes, and then we are going to, in ANSYS, we are going to see, say in this example here, it's going to say, okay, mode 1 is this, and the natural frequency for mode 1 is 109 Hertz, for example. And please note that in this picture here, I don't know if you can see it, but in this picture, this box is of the order of 100 millimeters, and you're seeing displacements of 960 millimeters. So in a modal analysis, when we plot the mode shapes, we do not pay any attention to the magnitudes over here. Why? Because the right-hand side of the equation is 0. There could be infinite number of possibilities that will satisfy this. So we do not pay any attention to the magnitude of displacements. We just look at the mode shapes of this. And if you would like to get real magnitude of any excitation, then you have to take it a step further and do either a transient dynamic analysis or do a harmonic analysis. So the only thing that we get out of the mode shape plots is we get the mode shape and the natural frequency. Like mode 1 is 109 hertz, mode 2 is 202 hertz, mode 3 is 249 hertz. So then the question is, how can we do a damped modal analysis? How can we bring damping into the system? Then the equation is modified such that we have mass matrix times U double dot, and then we bring in the stiffness matrix and also the damping matrix over here. When you bring in the damping matrix, then the eigenvalues become complex. The imaginary part of the eigenvalues are the natural frequencies, and the real part of the eigenvalue is a measure of stability. Positive means it's unstable, negative means it's stable. Okay, so these are, this is what we are seeing over here. It's stability, negative means it's a stable natural frequency. So the complete expression for the damping matrix is really here. You can have mass damping and you can have stiffness damping, and that the mass damping is usually referred to as alpha damping. Stiffness matrix is usually referred to as beta damping. And how do we input these alpha and beta values? We input alpha. It can be input as a material dependent damping value, meaning that we go in workbench, we go under the material properties, and then input an alpha value and a beta value under each material. This is the example here of structural steel. Or we can input as a global damping value. And that is done not as a material property, it's done as under analysis settings. Under analysis settings, you can input alpha and beta values over there. So that's how we can specify damping in a modal analysis. Okay, so after the modal analysis, we have an option. We can go to a transient dynamic analysis or a harmonic frequency simulation. So let's look into the next step. Let's assume that we are going to do a harmonic analysis. Now that we have determined the natural frequencies, how can we do a harmonic analysis? So in a harmonic analysis, used to determine steady-state response of a structure to the loads that vary sinusoidally or harmonically with time. And again, in workbench over here, you will see that this harmonic response is what we can use to do a harmonic analysis. So the inputs are harmonic loads, forces, pressures, imposed displacements, where we know the magnitudes and the frequencies. And we may have multiple loads at the same frequency. Most types of applied loads can be in phase or they could be out of phase. And the body loads can only be specified with a phase angle of 0. Those are the inputs. So what are the outputs? We look at displacements as a function of frequency. And we can also look at stresses and strains. And these are usually evaluated at peak response frequencies. So assumptions, the entire structure has constant or frequency-dependent stiffness, damping, and mass effects. No nonlinearities are permitted. So harmonic analysis is a linear simulation. If you specify nonlinear material properties, they will be ignored. I mean, you will be able to specify them, but they will be ignored. Transient effects are not calculated. To calculate the transient effects, we have to solve the problem in time domain. Acceleration and bearing loads are assumed to be real, meaning that in phase only. So all the loads and displacements vary sinusoidally, and like we said, all outputs are assumed to occur at the same frequency. So the calculated displacements are going to be complex if damping is specified. Just like the modal analysis, if we specify any damping in a harmonic analysis, then the displacements will be complex. Or if the applied load is complex, meaning that if the applied loads include a phase angle, then the displacement solution will be complex. So the governing equation for a linear structure that we are going to solve in harmonic in a frequency domain is going to look like this: mass matrix times acceleration, damping matrix times velocities, and stiffness matrix times displacement is equal to forces as a function of frequency. So if we assume forces and displacements are harmonic, then the solution will also be in harmonic. It will also be harmonic. So as you see here, once you figure out the math, meaning that take the first derivative and then take the second derivative of displacement, you see that the imaginary solution is associated with the damping matrix C over here. So that is why when you specify any damping in a harmonic response analysis, the solution will be complex. And also, on the right-hand side, if you specify anything with a phase angle, then the solution will be complex as well. So this equation, which is the equation for harmonic analysis, can be solved using one of the two methods. You either do the full harmonic response analysis or you do mode superposition response analysis. What's the difference? Full harmonic response solves a system of simultaneous equations directly using a static solver designed for complex arithmetic. So this is where the full harmonic response analysis treats the mass, damping, and stiffness matrices as a complex stiffness matrix, and the displacements are treated as a complex displacement, and the forces similarly are treated as complex. So then this equation is reduced down to this form over here. In a mode superposition analysis, this expresses displacement as a linear combination of mode shapes. So please note, full harmonic analysis is it's a straightforward solution, and mode superposition analysis is going to depend on the number of modes that you pick. If you don't pick enough number of modes, then the solution may be off, and it may be way off. So the full harmonic analysis is an exact solution. And since it's an exact solution, it generally is slower than mode superposition, and supports all types of loads and boundary conditions. And solution points may be uniformly distributed across the frequency domain, and solves the full system of simultaneous equations. And we can also specify damping in full harmonic analysis. And if we specify damping, then we can specify them as material damping. And we can, and as you see here, the damping can be in terms of alpha damping, beta damping. Alpha damping is going to affect the mass matrix. Beta damping is going to affect the stiffness matrix. And we can have element damping, gyroscopic damping, viscoelastic damping. All of these can be input as either a material-dependent damping value, meaning that for every single different material you have in your assembly, you can specify either an alpha value or a beta value, or you can specify a constant damping coefficient over here. Or you can directly specify as a global damping value under analysis settings. Instead of specifying for material by material, under analysis settings, you can say, okay, here's the global damping value. And so the loads could be gravity. In a harmonic analysis, you cannot specify gravity or thermal loads. It needs to be as a function of, in terms of forces, as a function of frequency or displacements. So we are solving after. If we do not pick the full harmonic solution, then the second option is mode superposition. And this is faster than the full solution. Why? Because we are picking a few mode shapes to approximate the result. For example, mode 1 plus mode 2 will give us the total modes over here. So it depends, the solution is going to depend on how many modes we pick. And we can pick a modal system to harmonic response by just doing a modal analysis first, then follow that by a harmonic response analysis. Then that we have to do, if we are doing mode superposition, we have to follow this procedure. Why? Because then the mode superposition is going to go back to modal and say extract the modes, either the first couple or the first 10, depending on however many we pick. So under the solution method is where we pick mode superposition. And how to specify damping in mode superposition harmonic analysis, we can specify them under analysis settings. So the last chapter I'd like to cover is the transient dynamic, meaning that so far we have seen how we have applied harmonic response simulation, meaning how we solve the problem in frequency domain. Now we are going to solve the problem in time domain. So transient dynamic analysis is a technique used to determine dynamic response of a structure under the action of any general time-dependent loads. This procedure is also known as time history analysis or transient structural analysis. And here we can include inertia and or damping effects. We can include any type of nonlinear effects. That's the most important, well, one of the most important things about transient dynamic analysis is we can include nonlinear contacts like frictionless or frictional contacts. We can account for material plasticity, hyperelasticity, creep, and also large deflection. And we can use it to determine the time-varying displacement, stresses, strains, and forces. This is typically a lot more involved than a static analysis. So transient dynamic analysis, we need to account for a lot of things that we do not account for in a static analysis. So what are those? For example, initial conditions. What are the initial conditions of a transient dynamic analysis? Do we all start from zero, or do we start from a certain velocity? Maybe the structure is moving in space with a certain velocity. So all of these can be accounted for here. Some hints for preliminary work to understand the physics of the problem. Usually, as engineers, we tend to jump into the most complex simulation. But before we jump into any complexity, we should try to solve and simplify and analyze a simpler model so that we kind of know what to expect from a more complex model. If nonlinearities do exist, first assess their effect using a structural analysis, using a static structural analysis. It may be possible to eliminate nonlinearities in the dynamic analysis. The questions to ask are is large deflection really important? Are the contact nonlinearities important? Is the material nonlinearity important? Maybe the material is going through plasticity at a very tiny area that it may not be that important, that it's not affecting the overall stiffness by much. So, and then of course, excuse me, we need to do a modal analysis to assess the dynamic behavior. And first we have to do a natural frequency and mode shape analysis. Why the natural frequency is going to be useful in calculating the initial time step, So as we have seen before, this is the equation that we are solving. It's the full equation that we are solving, and the stiffness includes all the nonlinearities. And so I'm going to skip through these. Just like in the harmonic analysis, there are two ways to solve this in transient dynamic, the full method and the mode superposition method. The full method, keep in mind, it allows all types of nonlinearities, whereas the mode superposition doesn't allow all types of nonlinearities. And in the full method, just like in harmonic response analysis, we are solving the full equation of motion, whereas in the mode superposition method, we are picking a few modes and we are doing a much faster simulation, just like the example that we have seen in the harmonic response analysis. So, so I'll skip through these here. And then in terms of, what we can account for in a linear analysis, force is related to the displacement by the stiffness matrix over here, and it's linear. It doesn't matter where we are, we get a linear solution. In a nonlinear analysis, force and displacements are not linearly related, so there's a nonlinear relationship between the force and the displacement. To solve these matrices, nonlinear stiffness matrix, we do Newton-Raphson method. We use the Newton-Raphson method, and that means when I say we, ANSYS uses the Newton-Raphson method, and to account for these structural nonlinearities. First is the geometric nonlinearity, then we have material nonlinearity, and we have contact nonlinearity, and that is the frictional and frictionless contacts. So all 5 contact types are allowed, meaning you can have frictionless, rough, frictional contact. The last 3 contacts here are what's considered nonlinear contacts. Bonded and no separation contacts are designated as linear contacts. So the way the Newton-Raphson method works is it basically whenever you apply a force, it takes that full force and then applies it, and it finds the displacement. Now, at that displacement, through internal equilibrium equations, it says the force cannot be the applied force. It has to be F1. That's the internally calculated force. So it brings it down to F1 level. Then at this level, it finds the tangent modulus, the tangent stiffness, and then it applies the full load again. And then through equilibrium iterations, it says, okay, I cannot be there at the fully applied load. I need to be over here, which is, let's say, F1 prime. So it does this until it reaches convergence. So this Newton-Raphson method is what we use, and this Newton-Raphson method is also can be it helps for Newton-Raphson method to reach convergence if we specify load steps and sub-steps, meaning that if we are applying 50,000 pounds on a structure, we shouldn't really apply 50,000 pounds just at the first load step. Maybe we should apply 1% of that. So in a dynamic analysis, we should always look at the real dynamic history. What is the load that we are applying and how does it change as a function of time? So those are really important in transient dynamic analysis, and we cover these. We have a 2-day dynamic class. We cover all of these in our 2-day dynamic class. So you know, you're welcome to attend our classes here. We currently have a mechanical class going on right now in our office, so I just want to reiterate on this. You can check our class schedule on www.ozeninc.com under training, and you will also see our free webinar schedule. So next week's webinar is the turbulent flow with ANSYS CFD, and the week after that is fracture mechanics. So at this point, you know, I'm going to take on any questions you may have, and I'm just checking the box over here, the chat box, so feel free to type in any questions. So there's one question here. It says, how do we calculate the initial time step size? The initial time step size in a transient dynamic analysis is calculated with the formula delta T is equal to 1 divided by 20 times the natural frequency. So delta T is equal to 1 over 20 times the natural frequency. So that's you know, that's how we calculate that. So another question is, what nonlinearities are allowed in response spectrum analysis? In a response spectrum analysis, there's really no nonlinearity because it's all linear. So one thing that could be done is if you do a static structural analysis, and then you can see if you can bring in that response spectrum analysis. But in general, you know, in a response spectrum analysis, everything is considered to be linear, and that you know, we kind of, if I go back to the to this over here, in this chart over here, response spectrum analysis, there are really no nonlinearities allowed here. So so that's so if we want to do again, if we want to account for any nonlinearity, we have to do a transient time domain simulation, which means transient structural analysis over here. Okay, so I don't see any other questions, so thank you for attending. So there's one, let me see here. There's one more question here, but I can't seem to. For transient analysis, damping ratio has to be mass or stiffness damping. For transient analysis, damping ratio has to be mass or stiffness damping. So for transient analysis, we can specify either a mass damping or a stiffness damping, or we can specify both. So please note that if you specify mass damping and stiffness damping, the results are cumulative, meaning that mass damping will add linearly to the stiffness damping. And on top of that, if you specify a global damping value, that will also be cumulative, meaning that now you have mass damping, you have stiffness damping, and then you will have global damping. That will, so one thing is you may want to make sure you're not damping the structure a lot. So you may want to check on your damping values. So what's a good damping value that you can use if you don't know what the damping values are? We typically use anything from 1 to 3 to 5%, 5% being max. But typically 1 to 3% is a good damping value that can be used for metallic structures. Anything else that may be too much. So, okay, well, I'll stop the recording